The Large Hadron Collider will reopen today after 3 years of being shut down for improvements.
CERN has made headlines yet again. The renowned Laboratory for Particle Physics has announced a rather unprecedented discovery.
Scientists at the CERN Nuclear Research Centre in Switzerland have succeeded today in producing record-breaking high-energy particle collisions
Made by their Large Hadron Collider that may likely cause a shift in our understanding of the universe. Scientists have reported that these anomalous readings could signal the existence of extraterrestrial life in a parallel universe. In this video, we will be discussing the just-announced CERN discovery that changes everything. Number 1. The chilling discovery. In a recent experiment with the Large Hadron Collider, CERN scientists noticed something strange with a particular kind of quark. Quarks are the building blocks of all matter, and are of different types. Physicists call the different types flavors. Some of these so-called flavors of quarks were extremely unstable and decayed rapidly. The subject of this particular anomaly was the beauty quark, which has an average lifespan of 1.5 trillionths of a second. It turned out that the quark's decay pattern was radically different from what scientists predicted based on the Standard Model. Based on their predictions, when a beauty quark decays, it should be influenced by the weak force and transform into what is called leptons, which is a set of lighter particles, either an electron or a muon, with the Standard Model predicting a 50-50 chance for both particles. But what the data from the Large Hadron Collider was showing was relatively different. The data showed that these quarks decay into muons only 70%, as often as they decayed into electrons. This was especially attention-worthy because electrons and muons are carbon copies of each other. The only difference is that the muon is 200 times heavier. Still, it should not affect the rate of transformations. All the forces within the Standard Model are supposed to pull on these two particles with equal strength, and because the beauty quarks decay through the weak force, both should result from the transformation the same number of times. There is only one way for this anomaly to occur: if a new type of particle that has never been seen before gets involved with the process. Some researchers have been made to speculate that some new type of physics could be at play. A new force-carrying particle should mean brand new physics, which could expand the Standard Model and answer many unanswered questions. Number 2. The possibility of new physics. Currently, we do not have many ways to probe particles, so the theory of the Standard Model is our best understanding of how the strange world of particles behaves. The Standard Model is
In just 7 seconds a day, this strange candy can cleanse 2.5 ounces of mold from your
scientific framework that describes everything we know about the building blocks of the physical world with pinpoint accuracy. But the shocking thing is that, even with this relatively high level of accuracy, physicists are well aware that this model still needs to be completed, and plenty of pieces still need to be added to the reality puzzle. Out of all the fundamental forces, the Standard Model can only describe 3: the electromagnetic force, the strong force, and the weak force. Currently, it has no description of the force of gravity, and no explanation for the dominant form of matter in the universe, dark matter. During recent experiments, researchers noticed an anomaly within the data they were analyzing that did not correspond with what is known within the Standard Model. Even though it is not generally uncommon to find results outside this model with the sheer amount of data that the LHC puts out, this time, however, something has caught the attention of scientists, and they knew that they needed to take a closer look to discern this new phenomenon. Number 3. What could this brand new force be? To explain this unprecedented discovery, the researchers have considered that there may be a new fundamental particle, which they have called Z prime, which is a brand new force-carrying particle. And even though this force is more than likely to be extremely weak, because there have been no signs of it until now, according to the researchers, this force would interact with electrons and muons in different ways. But the extent of its interactions with the particles of the Standard Model remains a mystery for now. This would be a breakthrough that physics has been waiting decades for if they found new force-carrying particles. Physicists are hopeful that if this discovery is confirmed, it could help unlock established mysteries of the universe and answer age-long questions like what dark matter is, or paint the full picture of the Higgs boson's role in creating our reality. Some scientists have come up with a theory that this unknown force may help achieve one of physics' biggest goals for the past century, to unify the fundamental forces of nature. Number 4. The Large Hadron Collider CERN, which is the European Council for Nuclear Research, has been carrying out astonishing experiments since the organization first came into existence in the mid-50s. They have been brought into the spotlight numerous times for various reasons, good and bad. The different experiments that they have carried out have brought mixed feelings among people. Some of their experiments have sparked fear of the possible creation of black holes, rips in our reality, and a host of other theories due to the huge size of the organization's funding and the nature of their research. Of all their experiments, one of the most famous and controversial achievements which stands out even to this day came when the Large Hadron Collider was constructed. The Large Hadron Collider, the largest particle accelerator in the world, spans over 27 kilometers in circumference and costs over $4.5 billion. That's a huge amount of money. However, even with this ridiculously large sum of money, many positive supporters of CERN's experiments would argue that the money was well spent, because the LHC, since its construction, has led to some of the most groundbreaking discoveries of the past few decades. One such eye-opening discovery is the discovery of the Higgs boson, which, strangely, is also called the God particle, and many other particles that, before their discovery by the LHC, had never been seen before. This massive LHC can accelerate various particles around and around the loop. It does this until the particles travel near the speed of light and complete over 11,000 laps per second. How did they achieve this? They accomplished this with extremely powerful electromagnetics, creating a magnetic field within the accelerator. This magnetic field is more than 100,000 times stronger than the magnetic field surrounding Earth. But only some people are fans of science, especially not science, which seems as controversial as the experiments at CERN. Some people have been wary of the effects of generating a magnetic field of this magnitude on electronics in the local area, and even the effect it would have on the Earth's magnetic field. Let's hope it doesn't tear it down. When these particles get to their top speed, which is 99.9999991% the speed of light, the particles traveling in opposite directions are forced to collide with one another, resulting in a powerful collision to release massive energy and an assortment of particles. The LHC was built with the ability to accelerate a variety of different particles. This will allow researchers to see different particles arise after the impacts. Number 5. What Elon Musk has to say. According to Musk, between 1998 and 2008, the Large Hadron Collider, the largest and highest energy particle collider in the history of mankind, was constructed by CERN. This process was done with the assistance of more than 10,000 scientists, hundreds of universities, and laboratories from over 100 countries. It is located in a tunnel with a 27-kilometer circumference. The border between France and Switzerland, close to Geneva, is about 175 meters below ground. The energy of the first collision recorded in the Large Hadron Collider was 3.5 tera-electron volts per beam, which is nearly 4 times more than the previous world record. And that is not all. After the LHC was further enhanced, the energy went as high as 6.5 tera-electron volts per beep. Musk stated that proton beam collisions are what the Large Hadron Collider does best. But in addition to that, it can speed up beams of heavy ions, especially lead ions. Pro-photon and lead collisions are usually carried out for 1 month each year. The primary objective of the Large Hadron Collider is to allow physicists to test the predictions of many particle physics theories. It is worth noting that they are looking for the enormous family of new particles predicted by subatomic particle theories and measuring the features of the Higgs boson. Hadrons are subatomic composite particles consisting of quarks, and are bound together by a strong force, similar to how the electromagnetic force holds atoms and molecules together. Baryons like protons and neutrons are some of the commonly understood hadrons. The pion and chion mesons, first identified during cosmic ray tests in the late 1940s and early 1950s, are also included. The LHC brings two opposing particle beams together so they can collide. Number 6. A particle explosion. When these particle collisions eventually occur, it would result in a shower of particles whizzing out in all directions. These particles have a relatively short lifespan. Most of them stay in existence for a fraction of a second or millisecond before decaying out of existence into nothingness. By varying the types of particles, researchers can discover new particles in these flurries. With the help of specially designed technology, supersensitive detectors are placed around the collision sites to prevent the loss of any information from every collision. And this massive amount of information adds up and requires a huge amount of time and manpower to sift through. The experiments carried out at the LHC can create more than 15 petabytes of raw data from these collisions every year, which the scientists then meticulously comb through to sort out the data they are looking for. The LHC achieved a significant milestone in 2017 when scientists permanently put over 200 petabytes of data into its tape libraries. To put this massive amount of data into consideration, it would mean that 1 petabyte worth of data is equal to around 250,000 movies. Number 7. The Higgs boson. The Higgs boson is said to be an elementary particle that is associated with the Higgs field. It is the quantum excitation of this field. It's just like the same way you see ripples in the sea. The boson itself is like a completely new kind of animal amid other animals in the zoo of particles. It has neither the quantum properties of elementary matter nor those of the carriers of quantum interactions, such as electromagnetic force, weak force, or nuclear interactions. The Higgs boson was discovered at the Large Hadron Collider, a groundbreaking discovery made simultaneously by the two large multi-purpose experiments, ATLAS and CMS. It was announced on the 4th of July 2012 at CERN. At the time, the new scalar boson was observed mainly in two rare decay channels, which offered the cleanest signal. The decay was observed in a pair of photons, which involved a purely quantum virtual process, and the direct decay in a pair of Z bosons, the carrier of the neutral-weak interaction. The discovery of the Higgs boson at that time may have completed the Standard Model, but this wasn't the end of investigating this elusive particle. One of the significant discoveries made since 2012 involved confirmation of the decay of the Higgs. According to CERN at that time, the investigation of this elusive particle will deepen during the third run of the LHC, particularly when the particle accelerator's high luminosity upgrade is completed in 2029. This will allow the LHC to conduct more collisions, providing researchers with more opportunities to spot exotic physics, including phenomena beyond the Standard Model. CERN has estimated that as the accelerator is upgraded each year, it will create 15 million of these particles. This is compared to 3 million Higgs bosons created by the LHC in 2017. This may be key to detecting other flavors of the Higgs boson. Theories that go beyond the Standard Model of particle physics also predict as many as 5 different types of Higgs boson, which may be produced less frequently than the primary Higgs boson. Even before the upgrades, scientists have already provided strong evidence of a magnetic Higgs boson. But what is so important about this Higgs boson anyway? This Higgs field played an extremely important and decisive role in the first moments after the universe's birth. It determines the very nature of the vacuum which fills our space-time. It is why matter and interactions exist as we know them, and it is responsible for the appearance of the mass of all known elementary particles. Without the Higgs field, and thus without the Higgs boson, there would be no atomic elements, stars, or life in this universe. Number 8. Why is the Higgs boson called the God particle? The Higgs boson's moniker, the God particle, was strengthened upon its discovery due to popular media. The origin of this is usually linked to Nobel Prize-winning physicists who had referred to the Higgs boson in frustration as the goddamn particle, with regards to how difficult it was to detect. According to Business Insider, when Letterman wrote a book on the Higgs boson in the 1990s, he had wanted the title to be The Goddamn Particle, but the publishers refused and changed this to The God Particle. That was the beginning of a troublesome connection between the particle and religion, which still bothers physicists today. Still, it's hard to overstate the importance of the Higgs boson and the Higgs field because only particles would have mass with this aspect of nature. That means there would be no stars, no planets, and no people, something which may be a little justification for its hyperbolic nickname. Number 9. Why do some scientists still study the Higgs boson? Besides the obvious necessity to perform the most precise characterization of the new particle, there are two main reasons why scientists still study the Higgs boson. First, they want to understand how the physical vacuum in which we live was created in the early universe. Secondly, they want to understand how this physical vacuum can be made stable. The Higgs field is unique, providing a non-zero mean expected potential energy to the physical vacuum. In essence, this is what makes the whole difference for our universe. Scientists believe that there is a possibility I'm accessing the shape of the energy potential, which is responsible for the very existence of the electromagnetic force of infinite range and the weak force acting at very short ranges. To do this, scientists must study how the Higgs bosons interact with themselves. And for this, they need to produce pairs of Higgs bosons. The Higgs boson helped solve the important question of the origin of the mass of all other elementary particles. However, its mass is yet to be explained. Any symmetry of the theory does not protect this mass and brings unwanted instability, to such an extent that through quantum processes, the physical vacuum itself could become destabilized by quantum fluctuations. Fortunately, this is on timescales, which is considerably larger than the known lifetime of the universe. But scientists are still looking for additional Higgs boson-like particles that would signal the existence of the new physics that is needed to stabilize the Higgs boson mass. All these factors motivate the analysis of much more data and, if possible, access to higher collider energies. This is why thousands of scientists worldwide are still dedicated to the task even after 10 years. Number 10. Why did it take so long to discover the Higgs boson? The Higgs boson was proposed in 1964 and discovered in 2012. Science enthusiasts have wondered why it took so long. It is because the Higgs boson is both heavy and extremely unstable. To produce such a heavy particle, the scientists had to concentrate a considerable amount of energy in a small volume. They needed a high-energy collider. Once the Higgs particles are produced, they decay in many different ways, and only a small fraction of them can be distinguished from the common background. Scientists constructed the largest and most complex detectors to identify such particles. Then, they analyzed hundreds of billions of proton-proton collision events to extract a Higgs boson signal. Number 11. Could CERN have opened a dimensional portal? Question remains. Will CERN's projects and discoveries help us make bold discoveries? Or will it send us to meet our ultimate demise? Conspiracy theorists have three popular theories regarding what CERN is really up to. The first and scariest theory, which caused people to point accusing fingers at CERN, is that CERN is trying to open a portal leading to hell. Some people believe that CERN's tampering with subatomic particles traveling at the speed of light will lead us past the gates of the ultimate fire. However, CERN has clarified that its goal for creating antimatter is to understand matter and mass better. The encyclopedia has defined antimatter to be subatomic particles with the reverse electrical charge of matter. Those who support the Big Bang theory think that antimatter was created during the universe's formation and should represent matter equally. But on the flip side, antimatter is very rare. The second CERN conspiracy theory is that of the Mandela effect. The Mandela effect is simply a phenomenon when many people remember an event from the past occurring differently than in reality. Some conspiracy theorists think CERN's particle experiments will likely cause shifts in our reality and push our world into an alternate dimension, creating a large-scale Mandela effect. Third and finally, some conspiracy theorists believe that human sacrifice happens on-site at the CERN complex. A video supposedly appeared online 2016 claiming that ritual sacrifices were happening at CERN. The video supposedly showed several cloaked figures walking around the grounds of CERN. It was speculated that the footage captured a young girl being stabbed in the chest by the cloaked figures. According to The Guardian, at the time, a CERN spokesperson came up to debunk the claim, saying that the ritual was staged as part of an elaborate prank. The question of whether police investigation took place after that is yet to be answered. It is no news that CERN has been a long-time target of conspiracy theories. Thus, it's no surprise that on July 5, 2022, when scientists resumed activity after 3 years of completing upgrades and maintenance, conspiracy theories would also show their faces online. While science hopefuls may find this news disappointing, it is clear that CERN has no plans to open a portal to hell, the future, or any other dimensions. Number 12. Ghost particles detected. Beams of protons keep whizzing around the 27-kilometer loop of the world's largest particle accelerator, more than 300 feet underground. For over a decade now, its ability to smash particles together at extremely high energy has been helping humanity peek into the virgin frontiers of physics. FASIR, the forward search experiment detector at the LHC, has achieved an unexpected goal. For the first time, it spotted high-energy neutrinos created by a particle collider, detecting 153 events that were neutrino interactions with extremely high certainty. This significant milestone in particle physics could help scientists deepen their understanding of highly energetic neutrino interactions in the universe and unravel the secrets of how stars burn and explode into supernovas. Neutrinos are tiny subatomic particles that are found almost everywhere. Every time atomic nuclei combine or break away, neutrinos come into existence. They are produced by cosmic rays and radioactive decay in particle accelerators and nuclear reactors on Earth, and even in a banana, from the natural radioactivity of the potassium in the fruit. However, these massless and chargeless particles are the ultimate cosmic ghost. Once produced, they rarely interact with matter. About 100 billion neutrinos pass through each square centimeter of our body every second, but they are so elusive that we can't even feel them. This elusive nature earned them the nickname ghost particles. Scientists have been chasing them since they were first seen zipping from a nuclear reactor in 1956. Physicists first detected the signatures of 6 neutrinos in 2021, but it took them 2 whole years to finally collect enough data to conclude that these ghostly particles were real. James Boyd, a particle physicist at CERN and co-spokesperson for Phaser, explained that the ghost particles can tell us about deep space in ways we can't learn otherwise. These very high-energy neutrinos in the LHC are crucial and help us understand exciting particle astrophysics observations. The experiment will continue to take data until the end of 2025. Scientists expect to find more such ghost neutrinos and unveil the intricacies of physics that were yet to. Can the Large Hadron Collider trigger earthquakes? Earthquakes are natural hazards that are caused by the movement of tectonic plates. When these plates move towards, apart, or even past each other, they can lock up and build up stresses at their boundaries, such as the middle of the Atlantic Ocean or along the Pacific Rim. When the plates suddenly slip apart, this stress is relieved, which causes a release of huge amounts of energy, leading to an earthquake. The LHC cannot trigger earthquakes. Many earthquakes occur across the Earth each year, teaching several million, but most are too small to be detected without monitoring equipment. There is no way by which the LHC could trigger earthquakes, and there is no correlation between LHC operation and the occurrence of earthquakes. Some high-precision instruments at CERN can detect earthquakes due to their sharp sensitivity to tiny movements. In the LHC, there are more than 100 hydrostatic leveling sensors. These sensors monitor the displacements of the magnets that steer beams of particles around the LHC's 27-kilometer ring. These sensors can detect the waves emitted by earthquakes occurring very far away after their journey through the Earth. The precision laser inclinometer is another tool used to measure the movements of underground structures that can affect the precise positioning of the LHC's particle detectors. These are also sensitive enough to detect earthquakes. Number 14. CERN and its purpose. CERN is an acronym for the French Conseil Européen pour la Recherche Nucléaire, or European Council for Nuclear Research. It is a provisional body that was founded in 1952 and saddled with the responsibilities of establishing a world-class fundamental physics research organization in Europe. At inception, pure physics research was concentrated on understanding the inside of the atom, hence the word nuclear. Our understanding of matter today is wider. It goes much deeper than the nucleus, and CERN's main area of research is particle physics. For this reason, the laboratory operated by CERN is often called the European Laboratory for Particle Physics. Particle physics studies the fundamental constituents of matter and the forces that act between them. At CERN, the scientists use the world's largest and most complex scientific instruments. They use these to study the basic constituents of matter. We want to advance the boundaries of human knowledge by delving into the smallest building blocks of our universe. What will CERN uncover next, and what will it mean for the future of science? What are your thoughts on these discoveries? Do you think they can potentially affect us?